In this video, we're going to investigate a little bit more the idea of centripetal and tangential forces and accelerations. So I've chosen another pretty classic physics problem. This is a car traveling around a curve on a banked roadway. So this is a very poor, sketch of looking at the thing from above. So here's the dotted line is the curve around which the car is driving. This will represent the radius of curvature. Even if this thing doesn't make a complete circle, we can take this little section and model it as a circle and find out the radius through geometrical means if we need to. But it's going to have some sort of radius of curvature. So looking at this from above, notice this will be the tangential velocity. And the centripetal acceleration is going to have to be directed towards the center. And that's what centripetal acceleration is. But if the velocity of this thing is changing, then it's accelerated. And what is it doing? It's turning. We're going to assume that it's not speeding up, which means all of the acceleration is in the centripetal direction. Now, here is what it looks like from behind. And notice if I have to put my perspective down here and look at it this way. And so the tangential axis here is actually into the page. Because of that, I'm not going to worry about it here. We already assumed there was no tangential acceleration because I said it's not speeding up. So we can forget about the tangential axis here. But what I do want to find out is where is the centripetal axis here? And if I imagine that I'm looking at this from behind, and this thing is going into the page and then turning. As it goes through the page, it turns around the curve. From this perspective, it looks like the centripetal axis, that would be the direction of the centripetal acceleration, looks like that. Okay, so why do I need to know that? Because I need to know how to resolve vectors into components along my coordinate axes. When I did inclined plane problems, which is what this looks like, before, my strategy was always to rotate my x-axis from horizontal to lined up with the ramp. Then I rotated my y-axis from vertical to perpendicular to the ramp. But in this case, I'm not interested in x and y. I'm interested in centripetal. And that is actually lines up with what I used to call my old x-axis, right? The horizontal one. So when I resolve vectors into components, I'm going to base my coordinate system off this consideration, the centripetal acceleration toward the center. For this particular example, we're going to ignore friction. That is, we're going to assume the car is not sliding up or down the ramp. And we'll talk about that at the end of the video, why we can make that assumption and under what conditions that's valid. But first step is going to be to draw a free body diagram. Of course, I've got gravity coming down, and I've got the normal force like this. And it looks like I'm going to need to resolve my normal force into a centripetal component. Right there. So this is going to be my normal N sub C. I'm not using X or Y, I'm using C. And there's going to be another force of, another component of the normal force. Of course, put my N in the wrong place. We'll call this N sub Z. I don't really want to use X or Y, so we'll pick the other one, Z. So I have some sort of hybrid coordinate system going on where I have a centripetal axis, I've got a tangential axis into the page, and then I'm just going to call the up and down direction Z, just for kicks. And if I don't have any friction, it looks like this is the only thing that I have. These are the only forces that I have. And so if I sum up my forces in the centripetal direction, that's got to equal ma centripetal. And we're going to define it towards the center of the circle as negative. So this component is negative, and I'm going to get minus nc is equal to minus mv tangential squared over r. Remember, the centripetal acceleration is defined as negative. The convention there is that we're pointing towards the center of the circle as negative. You can change that if you want to, as long as you're consistent. I'm going to stick with this. As you notice, what happens is my negative signs go away anyway. All right, so I need to figure out what my normal component is. Just to remind you of how the geometry worked for inclined plane problems, let me go to another sheet. When we did inclined plane problems, we had usually something like this. where that was my normal force and this was mg, and there was a ramp here, and we figured out that this angle is theta. Well, if you notice, what I'm doing here is to resolve the components of the normal force, I either need this angle or this angle. This angle here between the normal force and the vertical is here, and maybe you can see these are both parallel lines, and so that's going to have to be theta there. So this is theta. So it looks like my centripetal component is n sine theta equal to mv tangential squared over r. Okay. All right. Now, of course, I'm probably going to need to unpack what the normal force is here. And so let me do the sum of the forces in the z direction. This one's going to be easier because there is no acceleration in the z direction. This is not going up the ramp or down the ramp. That was the assumption we made. And so this turns out to be 0. And I get n cosine theta minus mg is equal to 0. Run through the math. Looks like I'm going to get n is equal to mg over cosine of theta. I can then plug that back into here. And I'm going to get mg over cosine theta times sine theta is equal to mv tangential squared over r. Okay, I can lose the m's. Sine theta over cosine theta is going to give me tangent theta. Looks like I'm going to get g tangent theta is equal to v tangential squared over r. And I guess we haven't actually talked about what we're solving for. We're going to solve for the tangential velocity. I'll tell you why after I do it. V tangential is then going to be gr tan theta square root. So the assumption we made was that this car was not moving up the ramp or down the ramp. This is the specific velocity for which that is the case. On a bank of angle theta, at or near the surface of the earth, so we can use little g, and going around a curve with radius of curvature r, this is the specific tangential velocity at which I just turn without any effort on my part. That is, I don't have to turn my steering wheel. I don't have to depend upon any friction or anything to turn me, friction between the wheels and the surface of the road. I just turn. So if I drive into this curve and don't touch my steering wheel, but I'm moving at this velocity, my car just turns naturally. This is actually why they do bank curves. Next time you go around a curve, if you're driving or riding as a passenger, especially a pretty sharp curve, notice the roadway. It is actually banked. Not this extremely, of course, but it is actually banked, and that is to help you turn. You find the same thing if you've ever been to a NASCAR race. Those curves are really banked because they're moving at really high velocities, right? They move at really high speeds, but they help them turn. So the banked roadway actually just, this component of the normal force, because of the way the road is constructed, pushes you in the centripetal direction, and it actually helps you turn your vehicle. Now, usually, we're going faster than we can bank the curves, right? So we have to turn our wheels somewhat, but we don't have to turn them as much as we would if the road was flat. So this is actually an actual engineering way to build roads.